the big four come back again in rotational motion. Suppose we have a flywheel that's turning, and it's turning at so many radians or revolutions per minute or radians per second. And we want to know how long it takes to stop, for the wheel to stop, if I apply some kind of braking mechanism to it. Well, these are angular problems, but the big four can be used in a rotary form, in a rotational form. Same equations, different variables. So instead of using d for distance, I use theta, which is an angle, in radians. Instead of velocity, I use angular velocity in radians per second. And instead of acceleration, I use alpha, which is the rotational acceleration in radians per second squared as it speeds up. So instead of d equals 1/2 the average velocity times time, theta, the angular displacement, is the average angular velocity times time. So in other words, each of the big four has a rotary counterpart where we simply take the equations of the big four shown in blue that we know, 1, 2, 3, 4, and instead of distance, we put theta, instead of v, we put omega, and instead of a, we put alpha, and the equations are the same. Time is time, whether you're in rotating frame or linear frame. So here I have 4 new equations for free. I don't know why they spend so much time on this in class. You just have to say, you're smart, you get it. The big four can be used in rotational dynamics and kinematics as well as linear kinematics. All you need to do is change the variables. Instead of using distance, use theta. By the way, the relationship between these variables, the linear variable, distance, velocity, acceleration in linear terms, is the rotary variable times the radius. So if I have a mass up here and it's rotating through some theta, the rotary variable times the radius, theta times r, is d. Velocity is omega times r. You know that's true because suppose you have a road like this, you come to an intersection and you head down the road, a band, and so you have band members here playing instruments and they're going to turn the corner. This guy doesn't have to go very far. But if you want to keep a line, this guy has to run like a bat out of hell to make it all the way around this distance in the same time that this person does that distance, this person does that distance. The further away I get, the faster I have to move. So the velocity is bigger the further I get from the center of rotation. So linear guy is rotary guy times radius. So you have to remember. And the variables' names. Theta for angle, omega, which is like a funny looking W, or it looks like a person sitting down from behind, and alpha, which looks like a fish swimming to the left. It's the first letter in the Greek alphabet and the last letter in the Greek alphabet. So these are the relationships that allow us to now solve problems that are big four problems, but in terms of rotation. And we will do problems like that. We have yet to, we want to kind of finish off kinematics and then go solve bunches of problems together, because that's the way you get good at physics, is by solving problems, not by jawboning about physics. Yep, woof, woof, woof. You got to do problems.